Happy Thursday, everybody. Hopefully the quiz went well. We're going to continue today just on our topic of differential equations. And again, next week, the plan is actually that on Monday we're going to begin with a review for the Chapter 5 exam. We're not fully done with Chapter 5 yet, but that's okay. I want to get that exam in by the end of the quarter. So the exam next week is on Thursday. So we will have a review for that on Monday. And then we'll do some more stuff on separable differential equations on on Wednesday. But that information on the Wednesday is not going to be on the exam for Thursday. So again, just as a reminder, we began to talk about differential equations. A differential equation is an equation that involves some derivative of y. So it could involve the first, the second, the third. It involves some derivative of y. And the solution here, as a reminder, the solution of a differential equation is a function. It's not a number. And in fact, many times we can have multiple solutions. Okay. One way that we used to picture those solutions was that we had a slope field. Okay, and if you remember, a slope field was this everywhere. We could only do this when we were talking about a differential equation that only involved y prime. But the solution here, the idea is that the differential equation is like if I had y prime equals xy, the differential equation is a little bit like a GPS. My slope tells me what direction I need to go. So it's a little bit like a GPS, and depending on where I am, for instance, at 0, 0, the slope there is 0. At 0, 1, the slope is 0. At 0, 1, the slope is 0. At 1, 0, the slope is 0. But at 1, 1, the slope is 1. At 2, 0, the slope is 0. But at 2, 1, the slope is 2. So I end up with a bunch of arrows everywhere here. And then based on the arrows, I can begin to say, well, if I were to start here, where would I go? And the arrows tell me what direction I need to go, which helps me to trace out a solution. So if I were to start here, I would end up going up, coming back, okay, etc. And then I end up with what are called particular. This is a particular solution. And the place where I start in order to get that solution is called an initial condition. And we'll talk more about that a little later. Okay, so then we talked about, we talked a little bit about the order of a differential equation. So the order is the highest derivative that's in the differential equation. So if the highest derivative is just the first derivative, then we have a first order. So first order differential equation, it just involves y prime. Second order involves y double prime. It could involve y prime, and it could involve y, but it has to involve y double prime. Okay. And then we talked about these special kind of differential equations that are called separable. And a separable differential equation is one where I can get just a function of y times dy is equal to just a function of x times dx. And when we have that, we can integrate both sides, and we can then try to solve for y. So we looked at a couple of examples last time about that. Now, there's a special kind of separable differential equation that we're going to deal with today, but before we do that, I want to there's some language that you may or may not have run across before called proportionality. So I want to deal with this language in case you've never seen this proportionality. Okay, we say that two things are proportional. That actually has a very special meaning in mathematics. If I say two things are proportional, that means something very special. So, for example, if I were to say, so let me say, if I were to say A is proportional to B, okay, the way that we write that is we use a little tilde. We use a kind of a squiggle. A tilde B, that's how we write that. But what it means for two things to be proportional is that one of them is a constant times the other. A is proportional to B. What that means is one is a constant times the other. Okay? Typically, oftentimes we're talking about functions here. One function is proportional to another if one is a constant times the other. So let me give you some examples here. The change, for instance, if I were talking about rabbits, and I said the change in rabbit population over time is proportional to the population itself. Okay, the change in rabbit population over time is proportional to the population. What that means is the change, if we call the population P, the change in population over time, that's a derivative, is proportional to the population. In other words, the change in the population is a constant times the population. Okay? This actually makes sense because if the rabbit population is bigger, you're going to see more change because more rabbits are having babies. If the population is smaller, you're going to see a smaller amount of change. So this idea that these two things are actually proportional kind of makes sense. Another example of two things that are proportional is if I had, if I talk about the change in amount of radioactive material over time is proportional to the amount of radioactive material. So how much the radioactive material changes is actually, over time, is actually proportional to the amount of radioactive material. So if I call the amount of radioactive material A, then the change in the amount of radioactive material over time would be dA dt. And what I'm saying here, when I say that these two things are proportional, is I'm saying that one of them is a constant times the other. And in this case, that makes sense because if the amount of radioactive material that I have is a lot of it is going to be decaying over time, so this change is going to be higher. If the amount of radioactive material I have is small, then this thing is going to be lower. So it makes sense that one would be a constant times the other. You don't always have to have a situation where two things are directly proportional, where one's proportional to the other. You can have something that's a little more complicated. So let me give you an example. The force of gravity between two objects is proportional to the inverse of the square of the distance between them. Okay. So the force of gravity between two objects is proportional to the inverse of the square of the distance between them. In other words, if I have two objects and a distance between them, well, let's maybe call that x, the force of gravity, G, is proportional to, let's skip inverse for a second, to the square of the distance. So that would be x squared. The inverse is 1 over x squared. Sometimes when we talk about this, instead of saying it's proportional to the inverse, we'll say it's inversely proportional to the square of the distance between. So you can either say it's proportional to the inverse or it's inversely proportional to the square, and all that means it's proportional to 1 over that. So in other words, the force of gravity is some constant times 1 over x squared. That actually turns out to be true. And when you study physics, you'll get into that a little more, okay? So that's the idea of proportionality. So now what we're going to do is we're going to solve a differential equation that involves proportionality. It's a separable differential equation, and it's called a growth or decay equation. It's actually called an exponential growth or decay equation because the answer is going to be an exponential function, but we're going to get to that. Okay. In this case, the rate of change of whatever object I'm talking about, so we're going to just call that in general y, over time is always going to be proportional to the object itself, to y. So in other words, dy dt in this situation is going to be proportional to y, or we'll say dy dt is a constant times y. All of the examples that we're going to give for the rest of this time are related to this in some way. So what we're going to do is solve this differential equation. We're going to get a solution, and then that solution is going to apply to all of the examples that we're going to look at. So we actually don't have to keep solving this differential equation again and again and again. The solution will always look the same, and we're just going to apply it in a few different, very specific contexts. Okay. So to solve this, it is separable. So let's bring the y over here onto the left side, and immediately something should go off in your head. What if y is 0? Okay, so let's take a case. If y is 0, then the derivative of y over time would also be 0. And that would satisfy this equation, so that works. So now we're considering the case when y is not 0, so we can divide by it. So we're going to put y on the bottom, and we're going to put the dt over on the right side. And let's integrate both sides. So we get natural log of absolute value of y equals kt plus some constant. Now to keep consistent with the book's notation, I'm not going to call it constant c, I'm going to call it d. Now let's solve for y, so we're going to take e to both sides, and that'll get rid of the natural log over there. We get e to the kt plus d, which is e to the kt times e to the d, where d is any number. So e to the d is going to be, we're going to give that another name. Let's call that capital E. Okay, e to any number is any positive number. Now let's drop the absolute value. So we get any positive or negative number here. But if e were 0, that's actually this case. So let's bring all of those together in one case. And let's call that C times e to the kt. This is my general, so C can be any number. This is my general solution for this scenario when my rate of change over time is proportional to the original thing itself. The solution is y equals some constant times e to the some other constant times t. So we're going to look at several situations where that have this type of behavior, and we're just going to use this equation to get solutions. Okay. So let's take an example. So one example that works here is radioactive decay. Okay. So for example, if I start with some amount of plutonium, plutonium is actually a radioactive particle. And if I have some amount of plutonium and just let it sit, then over time, it ends up shrinking. I end up getting less plutonium. The plutonium changes into some other element. But it changes over a slow period of time. And it's radioactive because it emits certain particles. So the way that we measure, one thing that's consistent with radioactive particles is that it takes a certain period of time to get half of the original amount. And that certain period of time it takes to get half the original amount is called the half-life. I don't know if any of you are familiar with this. The half-life of a particular radioactive particle. So the idea is, for instance, if I started with 10 grams of plutonium, and then I look at how long does it take me to get to 5 grams, there's actually a certain amount of time that takes depending on the type of radioactive material that you're talking about. So in the case of plutonium, the half-life, the time it takes for you to get half of it, is actually 24,360 years. Okay, now, how people measure this is a different issue that I'm not going to get into right now. But if we started with 20 grams and went 24,360 years, we would end up with 10 grams at the end. Okay? So that is known as the half-life. And radioactive decay actually follows this type of growth and exponential growth and decay model. So the rate of change of the amount of plutonium you have over time is actually proportional to the amount of plutonium you have. So in the case when we're talking about radioactive decay, we can always use this equation, y equals a constant times e to the kt. It will always have that form. All we have to do is figure out how do we get c and how do we get k. Okay, so to give you an example here, let's say that I gave you the half-life of plutonium, and then I said if I start with 10 grams, how long will it take me until I have 1 gram? So how long do I have to wait for the plutonium to decay and decay and decay until I only have 1 gram of plutonium left instead of 10? Okay, so what we're going to do is we're going to use some pieces of information here. The first piece of information that we're going to use is actually how much plutonium we're starting with at the beginning. That turns out to be an important piece. So when time is 0, when I have 0 time here, like right now, y is going to be 10 grams. So what we're going to do is we're going to plug that in here. I'm going to plug in y equals 10 and t equals 0. And what you're going to see here is 0 times k is 0, and e to the 0 is 1. So what we get here is 10 equals c times 1. So that constant in the front is actually 10. And it turns out that constant in the front is actually always your starting number. You can remember that, or you can sort of figure that out anytime that it's given. But in this case, my c right here is actually 10. So I'm going to start with 10. Now, the place I'm going to use the half-life is I'm going to figure out, what that's going to tell me is that if I start with 10 and I go for time 24,360 years, I end up with 5 grams, right? I end up with half. So if I can solve this equation, that's going to let me figure out what this k is. I already know what c is. That half-life information is going to let me figure out what the k is. So let's solve this. Let's divide by 10. So we get 0.5 is e to the k times 24,360. Now we need to get rid of the e, so I need to take natural log of both sides. So 24,360 times k. So I'm going to divide by 24,360. So k is natural log of 0.5 over 24,360. Okay, and if I get my calculator out and just look at what that is, I'm going to take 0.5 and take the natural log of that, and then divide by 24,360, and I'm going to get a really small number, but that's okay. So it's negative 0.0000285. Let's just leave it like that. So my equation right now is y equals 10 e to the k 0.0000285 t. Okay. So that's my equation for this plutonium problem. Now I haven't answered my question yet. My question asks me, how long do I have to wait until I have 1 gram? Well, the way that I'm going to get that is I'm going to plug in 1 right here for y, and then solve for the time. So if I divide by 10, I get 0.1. Then I'm going to take natural log of both sides. And then just divide by that constant in the front, negative 0.0000285, and that's going to give me my time. So my time is, so let's take 1 over that number, times the natural log of 1, and the time turns out to be 80,922 years. Okay. So notice we had to find that c and find that k before we could answer any questions about the problem. Now, if instead of asking me how long would I have to wait until I have 1 gram, it could ask me a question like, how much would we have in 10,000 years? How much of that would be left in 10,000 years? Well, if I want that, all I do is I take my equation, which we figured out, and for time, I would put in 10,000 here. So I would have y equals 10 e to the negative 0.0000285 times 10,000. And I would just plug that in and see what I get. So I'm gonna do that here. Let's take 0.0000285. Let's make it negative. Times 10,000. and then I'm going to take e to that times 10, and it looks like I would have about 7.52 grams of plutonium. Does that make sense? So there are a lot of different radioactive isotopes that actually work this way. Now, sometimes I bring this up and then people start asking about radioactive dating. Radioactive dating is a very controversial technique. And if you're interested in my views on radiometric dating, you should definitely ask me. It's not generally a very good technique at all for dating substances, and like I said, it's very controversial. Okay, let's do another example here. One other thing that ends up being true, that ends up having a exponential growth and decay type relationship, is actually population growth. Okay, so let me give you an example here. So suppose today we have 100 fruit flies. Okay. And then in 2 days, we have 300 fruit flies. This is kind of disgusting, but. And then I were to ask, how many fruit flies would we have in 10 days? 10 days from today. So population growth, just like radioactive growth and decay, has an equation y equals c e to the kt. And so what we're going to do is we're going to take some of the information that we're given here in order to solve for the c and the k. And then based on that, we're going to answer this question. So let's start with today. Today at time 0, we have 100 fruit flies. So if we were to put in 100 equals c e to the k times 0, what you'll see again is the k goes away, and that constant c is 100. So we've solved for the c, given this information. And then in 2 days, when t equals 2, we have 300 fruit flies. So what we're going to do is we're going to say, okay, now we have 300 equals, we figured out that the c was 100 already, e to the k times 2, and that's going to let us solve for the k. So let's solve for k. Let's divide by 100, so we get 3 equals e to the k times 2. Let's take natural log of both sides, and the natural log gets rid of the e, so we've got natural log of 3 equals 2k. K is natural log of 3 over 2, which, if I calculate that, is about 0.549. So K is about 0.549. So what we have here is our fruit fly population is governed by 100 e to the 0.549 t. That's our general equation here. So now if I were to ask, how many fruit flies will there be in 10 days? What I'm just simply going to do is plug in t equals 10. So let's take 10, let's take our 0.549 number times 10, take e to that, and then multiply by 100. And what ends up happening is we have 24,226 fruit flies. Okay. So the key here is to, if in radioactive dating or, radioactive decay or population growth, recognizing that the overall situation is an exponential growth or decay. So we start out using this equation, and then we have to use the information given to get the C and the K. Let me do one more. I'll point out there's one more example at the bottom of page 364. So if you don't get to this, you can read it. If there isn't enough time in class, that's fine. You can read about this. This is actually example 5. But another thing that could be governed by an exponential growth or decay would be something like revenue or costs, profits that you make in business. So in this example, it says that a manufacturing company stops advertising, and it starts with initial sales per month of $100,000 per month. So that's the start. And then after, I'm sorry, not $100,000, 100,000 units that it's selling, like 100,000 pencils that it's selling per month. And then 4 months later, those sales drop to 80,000. 4 months later. And then it asks how much will they sell 2 months after that? So in other words, 6 months later. 6 months after they stopped advertising, how many things will they sell? They're going to sell less and less. How much are they going to sell at 6 months later? Okay, and they kind of have to tell you that this is an exponential pattern of decline. So we're going to use this equation, y equals c e to the kt. And again, we're going to use these pieces of information to get the c and the k. And then we're going to use this 6 months later issue to get to solve our answer. So when time is 0, we start with 100,000. As you can guess, that ends up giving you that C. That C is always going to be kind of your initial amount there. And then 4 months later, the sales had declined to 80,000. So when T is 4, that's 80,000. So let's solve for K and see what we get here. So if I divide by 100,000, I get 0.8 equals e to the 4k. So then we'll take natural log of both sides and divide. So k is the natural log of 0.8 over 4. Let's compute that. So 0.8, and we're going to take the natural log of that divided by 4, and we get negative 0.0558. So my equation here is y equals 100,000 e to the negative 0.0558 t. That negative is actually important because it tells you that stuff's going down. If you get a positive there and the numbers are going down, then you did something wrong. Now what I'm going to do is just take this information and I'm going to plug in, instead of plugging in 4, I'm going to plug in 6 and see what I get. So y equals here 100,000 e to that number times 6. And we're just going to plug that in our calculator and see what we get. So let's multiply by 6, take e to that, and then do 100,000. And what we get is about 71,554 units. So that's how many units, if it's decaying exponentially after stopping our advertising, that's how many units we would be selling there. Okay, so take a look at the homework for section 5.6. And we will, on Monday, we'll jump into some review for the exam on Thursday. And then on Wednesday, we'll continue some of the discussion about separable differential equations. Have a great weekend, everybody.